The precise definition of a limit, part 4. Now it's time to start looking at the actual definition and where it comes from. So far, we've been looking at different epsilon error bands and different delta distance bands. And we've been trying to make sure that for any epsilon band, we can find a delta band so that if our inputs fall within this band, then the outputs will fall within our epsilon band. So we want to make sure that our function is getting trapped between these bands. But that's not quite enough. We also want to make sure that no matter how small we make that error band, so as epsilon decreases, we're always going to find a corresponding delta, such that when we have that delta and x is within that band, we always get an output that's within the error band. So we want to look at what happens as epsilon is getting smaller and smaller. We want to make sure that we still have a delta band. So in this case, yeah, it seems like that limit probably does exist and that it's correct. Let's take a look at another example. Here, we still want to know, as epsilon decreases, is there still a corresponding delta? So let's take a look. So we're looking at epsilon decreasing, and at some point, our delta band disappears. So we're no longer able to have an input that will land us within this band. So for here, our limit is not going to exist. Or at least this isn't the limit for this particular function. So when a limit exists, it doesn't matter how small we make epsilon, we can always find a delta that will land us inside of the epsilon band. So let's try to come up with a definition of what a limit is. So first off, if we're trying to find a limit and we're trying to have these bands, we need our function to be defined. If we had some big gaps here in our function, then there's going to be pieces here where we have inputs that lead us to having no output. And we wouldn't be able to have bands there. So that would be pretty tricky. So this definition is really only going to work if we have a defined function. At least near A. So we have to be defined close to A. And we're actually okay if we have an open circle at A. We've seen that limits can still exist at open circles, so except maybe at A. And we're trying to find a way to say that the limit as x approaches A of f of x is equal to L. So we're trying to say that this is the limit. And we found that we can come up with these bands that as we get closer for our error band, we're still able to find a delta band. So, and we want to make sure that if we have that delta band, we're still ending up within that error band. So that's if the distance from x to A is less than some number, which we'll call delta, then we're guaranteed that the distance from f of x to L is less than some sort of epsilon. So we're showing that we can always find some sort of epsilon and delta band No matter how small we're making epsilon, we're always able to trap that limit within those bands. And more precisely, where did that go? That was definitely not supposed to still have all this text on top of it. Well, let's just remove all this random text. Oh, there we go. More precisely and mathematically correct, we have this precise definition of a limit. So let f be a function defined on some open interval that contains the number a, except possibly at a itself. Then we say that the limit as x approaches a of f of x equals L if for every number epsilon greater than 0, there's a number delta greater than 0, and that just means they're both positive, such that if 0 is less than the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. And this is the precise definition of the limit that you will want to make sure that you memorize, because when we start doing proofs, you'll have to state this definition, so you want to make sure you have it. A lot of people find that being able to sketch this picture helps them be able to remember this definition as well.